Hi, today we're going to talk more about these theorems, and we're going to illustrate the uniqueness theorem, this very first theorem. So here we're given the moment generating function as e to the power of t times mu plus sigma squared times t squared divided by 2. If you look at the above table, that corresponds to a normal distribution. And that normal distribution has parameters mu and sigma squared. So this is going to be normal. If we see that moment generating function, we know it comes from a normal distribution, is going to be normal with parameters mu, and the variance is equal to sigma squared. And by the way, that is the mean right here. Okay, so that is an example of the first theorem. The second example here is concerning transformations. Okay, so here we have x1 is normal with mean 2, variance 1, and x2 is independent of x1. It has mean 3 and variance 5. Our goal is to determine the distribution of y equals 4 plus 3x1 plus 2x2. So in the setting of the theorem above, n is equal to 2, a0 is equal to 4, a1 is equal to 3, and a2 is equal to 2. One more piece of information is we could write down the moment generating functions of each, and it's going to have exactly that form, e to the t times mu plus sigma squared times t squared over 2. So let's take this a step further. And write that information down. Okay. So let me just erase all of that. mx1 of t, that is e to the t times the mean, so the mean is 2, so 2t, plus sigma squared is 1, so times by t squared over 2. Now the second moment generating function, mx2 of t, that has mean 3, so this is going to be e to the 3t, plus the variance is 5, so that will be sigma squared 5 times t squared over 2. Now, according to this theorem, the moment generating function of y, that's going to be e to the a0, that's 4, times by e to the 2, but we have to do composition. So let me take this one step back. So mx1 of 3t times mx2 of 2t. Because remember, we have composition, a1 is 3, a2 is 2, and it's the moment generating function of x1 composed with a1t. So mx1 of 3t times mx2 of 2t. So we'll have e to the 4 times the moment generating function we just wrote down, so e to the 2, but remember it's a composite, so t is replaced by 3t, plus t squared, that'll be 3t squared divided by 2. Now we have to do the same thing for the second moment generating function. This will be e to the 3t, but remember t is replaced by the composite of 2, so it should be this, times by 2t plus 5 times the composite of 2t, that's squared, divided by 2. Okay, now let's just combine this. They are all come under an exponent. So this will be e to the 4. And I apologize, there's one thing that should be done slightly differently, which is this should be a naught times t there. So this should be 4t. So 4t and now we're going to multiply by e, just figuring out the composites, so that'll be 6t plus 9t squared over 2 times by e to the 6t plus 5 times 4 will be 20t squared over 2. And now we can combine all these terms. This will be e to the 4t plus 6t plus 6t. So this will be 16t. Plus, we can combine the t squared terms. So 29t squared over 2. And we have now the moment generating function. This is exactly the form of e to the mu t plus sigma squared t squared over 2. So we'll conclude y is normal, and its mean here, its mean is this 16. So I'll put mean equals to 16. Then it has term of variance. Let's use purple. Okay. So that's the variance. And variance equal to 29. So that is the distribution of this transformation. Thank you very much.